All right, g'day. Welcome to the next one of these. Um, so in the last video, I was talking about how we were going to have to rebuild the models because of the mean split wasn't going to give us exactly even. It wasn't going to give us exactly even groupings, right? And we saw that the XGBoost algorithm takes into account distribution skew. So it was with the NRC data, which is made up of 90% null values, the algorithm was achieving an accuracy of 90%, but it was not significant. And essentially what the algorithm was doing was it was over predicting to the null value category, which is not what we want. What we're looking for are models that describe a real thing in the world. And that thing that we're looking for is how certain emotions are expressed sound symbolically. Um, Yeah, so we fixed that issue. Let me see if I can find the code for it. Um, by changing the mean split into a median split and then ensuring that our data was balanced. So here's the entire thing. And what we can do is take a look at our arousal classification counts. And we see down the very bottom here, we have two groups made up of 2,742. Now, these get fed into those k-folds. So certain k-folds are going to have less or more. They're going to have uneven samples, but because we're kind of aggregating those k-folds, then the effect of that unevenness shouldn't be a problem. You could, and I considered doing this, but I didn't, you could do this after you've done the k-fold splits, right? To ensure, or kind of as you're doing the k-fold splits, to ensure that each k-fold has an exactly balanced number of samples. But because we are aggregating those results, we're putting them all together, then there won't be, there shouldn't be, there won't be, there shouldn't be an effect. There shouldn't be an effect of distribution skew. And any distribution skew is going to be the result of randomization um, rather than inherently uneven distribution. Okay, so that was the problem. That's how it was fixed. The other problem that I came across, let me show you. It actually took up a bit of my weekend thinking about this and what the issue was and how it needs to be resolved. And I have resolved the issue, but we need to talk about some things and its impact on the algorithms. This is the feature importance for the 20 most important phonemes in the algorithm for the arousal model, right? So we have the vowel as the most important. Then if we look at valence, we have the vowel as the most important, dominance, concreteness, imaginability, familiarity, age of acquisition. All right. So alarm bells should be going off in your head right now because, all right, so these different psycholinguistic domains, why are they all returning the same feature importance? The same, like they're all kind of reporting that this one vowel is extremely important. The issue is that the R vowel is the most frequently occurring sound in American English by a long way, according to the CMU pronouncing dictionary. So it's really what this is capturing the effect of word length, the relationship between word length and each of these psycholinguistic domains, which is not what we're trying to capture. This is a problem. Now, we went over this effect in the second or the third video. I can't remember. Sorry, it's been a little while. And we talked about how word length was going to have an effect on the regression. Well, the thing is that decision trees use linear and logistic regression. So obviously that's what's happening here. So to explain it in simple English, this feature importance score isn't really a reflection of how well the val is communicating these psycholinguistic elements, what it is it's kind of a reflection of the relationship between frequency of occurrence and word length, where these sounds are more likely to occur in long words, right? So this is a real problem. We're not trying to explore that. I can do that exploration with a simple linear regression model. I'm not building an XGBoost algorithm to explore the importance of length, or the impact factor of length, right? So I resolved this issue in a kind of an interesting way, and I resolved it with this bit of code here. What this code does is it takes the number of phonemes in each word and it divides it by the length of the word, so the total phoneme count. So what we're trying to do is remove the impact of length. Now, this doesn't do that perfectly because of the number of null values in the data set, but it is the best solution that I was able to come up with, and it is certainly not ideal. Let me show you how what the data looks like when you do this. So instead of having phoneme counts, which are entire numbers, we end up with these fractions. Now, fractions are problematic in something known as gradient descent. In linear regression, we have these three formula. There is the linear regression formula, there is the cost function, and we have the gradient descent algorithm. What the gradient descent algorithm is doing is it's trying to find the bottom point of a valley, which represents the least square for that algorithm. Now, what happens is that you have what's known as a learning rate, and we have that learning rate. I can adjust that learning rate very easily with an XGBoost model, but it is a very difficult thing to do if you're doing it with regression. I think I might have posted on my personal website the code that I used for this. So what happens is essentially you take steps down one side of a mountain, increasingly smaller steps, and that is determined by your learning rate. When your variables are fractions, that has this effect on those steps, right? And what happens is down the bottom of this mountain, you get a valley, and then we get a rise up the other side of this mountain. And what happens is if you get to near the bottom of the mountain and you overshoot the valley, you overshoot the bottom point, then the gradient descent algorithm, what it does is it kind of turns you around and it sends you back. But this can result in this infinite bouncing, right, between sides of the mountain, and your algorithm never achieves convergence, right? And convergence is finding that the bottom peak, not the bottom peak. A peak is the top of a mountain, the bottom part of the valley. The bottom gully maybe. Anyway, fractions have a interesting relationship with that gradient descent algorithm. If I ran this, in fact, I tried when I ran this as a GLM, it failed to converge, and I got the failed to converge error message. There are ways of working around that. I don't want to do that. So I went and I created this data set. Now, with an XGBoost algorithm, what I can do is I can adjust that learning rate, which is represented here as the eta in the code, in the tuning code. However, if I was to retune this model, certain values of eta will fail to converge, and it will just never, it will just, let me show you. First of all, let me show you if actually, I can't show you. So what do we do? How do we fix this? My solution to this problem is to retune the model with a learning rate that I know will not fail to converge. And that learning rate, because I've been playing with this for the last couple of days, the learning rate that does not fail to converge is 0.1. So what I'm going to do is I'm going to manually set the learning rate for this model, but for every other hyperparameter, I'm going to let the model tune itself. And that's how we're going to avoid the convergence issue. Uh, yeah, I think that that's all I have to say for this. So I'm going to rerun all these models yet again. And I'll get back to you when we have some results. All right, take it easy.